A single teaspoon from one of these stars would weigh 1 billion tons. This is a magnetar, and its sudden tantrums unleash a cosmic domino effect that can reshape the galaxy. By the end of this, you will understand how one star's violent outburst can dictate the fate of worlds and even the birth of new solar systems. We will uncover how a crack in its surface can ripple outward to ignite star formation light years away, and whether its energy could probe the invisible dark matter that holds the cosmos together. What does it mean for our own world to exist in a universe capable of such raw, untamed power? To grasp its ferocious power, you must first understand its origin. A magnetar begins its life as the heart of a giant star, a core that has collapsed under its own immense weight after a cataclysmic supernova explosion. What remains is a neutron star, an object so dense that a single sugar cube of its material would equal the weight of every person on Earth combined. But a magnetar is a special breed. It is a neutron star pushed to an extreme, endowed with a magnetic field of almost incomprehensible strength. This field is 1,000 trillion times more powerful than the one that protects our planet. Picture the most powerful magnet you can conceive, then multiply its force by a number with 15 zeros behind it. This unimaginable magnetism does not lie dormant. It actively warps the very structure of the star, putting a death grip on its solid iron crust. The magnetic field twists and strains this surface, storing titanic levels of pent-up energy, much like winding a spring tighter and tighter. All that stored stress must eventually find a release. When the strain becomes too much to bear, the star's crust fractures. This is a starquake, a seismic event of cosmic proportions that tears open the magnetar's surface. The rupture unleashes a flash of radiation so brilliant it can outshine entire galaxies for a fleeting moment. This is the beast's roar, a foundational event that sets in motion a chain reaction felt across the void. This rigid crust is a lattice of iron, a crystalline shell under relentless assault from within. Think of it as a dam holding back an ocean of magnetic force, with hairline cracks spreading silently for years. The pressure builds until one final, microscopic shift becomes inevitable. The crust fractures. This is the starquake, a seismic snap that realigns the very skeleton of the star. The magnetic field lines, which were tangled and stored like colossal springs, violently break and reconnect. This reconnection is the engine of the flare. In that single, catastrophic instant, the magnetic field unleashes its pent-up fury, converting it directly into a firestorm of radiation. The flash is not merely bright, it is a fundamental reset, an eruption of pure force that marks the beginning of a journey far beyond the star itself. That first domino has fallen, and the chain reaction is now underway. The star's crust shatters, and the universe holds its breath for a millisecond. Then the dam breaks. A fire hose of gamma rays erupts, a hyperflare of pure energy that moves at the speed of light. This is not a simple flash, it is a directed beam of the most powerful radiation known. For that one blinding moment, this single object outshines every other gamma ray source across the entire observable universe. The energy released is so immense that if such a flare occurred within our own galaxy, even from tens of thousands of light years away, its radiation could punch through the void and temporarily strip electrons from atoms in Earth's upper atmosphere. This initial pulse is the first physical shockwave, a cosmic sledgehammer that smashes into the surrounding space. It carries with it not just light, but a storm of high-energy particles, all racing outward to trigger the next phase of a celestial domino effect. The true impact, however, lies in what this blast wave encounters on its journey. The radiation blast strikes the surrounding nebula like a cosmic tsunami. This cloud of ancient stellar debris, a remnant of the star's own explosive birth, is suddenly and violently illuminated. The gas and dust, once dark and cold, are flash-heated to temperatures of millions of degrees. For months, even years, this superheated material continues to shine, ringing like a bell struck by a colossal hammer. Astronomers observe this phenomenon as a light echo, a ghostly afterglow that expands through the nebula long after the initial flash has faded. It is the first visible sign of the Magnetar's tantrum, a cosmic fingerprint revealing the path of destruction. But the flare does more than just light up the neighborhood, it actively reshapes it. The sheer force of the radiation and particle wind pushes outward, sweeping up the surrounding material and carving out a vast, empty cavity around the star. This clearing effect is a fundamental reset for this pocket of space, altering the density and temperature of the local medium. The stage is now set, and the conditions for what might happen next, for the birth of new stars or the disruption of old ones, have been irrevocably changed. This local chaos is merely the beginning as the chain reaction prepares to travel much, much further. This expanding blast wave does not travel alone. As the initial gamma-ray fire plows into the cold, static gas of interstellar space, it forges a new kind of object in its wake. A cosmic fireball is born. This is not a simple ball of flame, but a rapidly expanding shell, a bubble of chaos containing a superheated soup of matter. Within this shell, particles are caught in a violent tug of war. The leading edge of the blast wave acts like a cosmic snowplow, piling up the thin interstellar gas and compressing it with unimaginable force. This collision creates intense shock fronts, walls of pure energy that race ahead of the main blast. These shocks are natural particle accelerators on a galactic scale. Through a process known as Fermi acceleration, charged particles bounce back and forth across these turbulent magnetic boundaries, gaining a little more speed with each crossing until they are hurled outward at velocities approaching the speed of light. This sustained emission is the blast's long-lasting echo, an afterglow that can shine for weeks or even months. Astronomers eagerly track this fading light across X-ray, optical, and radio wavelengths. Each frequency reveals a different piece of the puzzle. The X-rays tell us about the most energetic processes near the shock front, while the radio waves map out the distribution of material the blast has swept up. This glowing remnant is a cosmic autopsy, allowing us to dissect the properties of the explosion and the medium it traveled through long after the blinding initial flash has vanished from view. The story of the Magnetar's fury is now written in this expanding sphere of light, a message traveling across the cosmos for anyone who knows how to read it. These shock waves become the universe's ultimate slingshots. As the blast front plows through space, it acts like a natural particle accelerator of unimaginable scale. Within the turbulent chaos of these magnetic storms, protons and even entire atomic nuclei are caught. They bounce back and forth across the shock front, trapped by writhing magnetic fields. Each crossing imparts more energy, accelerating these subatomic fragments to velocities that dwarf anything produced in our most powerful human-built colliders. They are flung across the galaxy as ultra-high energy cosmic rays. Each one carries a tiny fragment of the Magnetar's immense power. This is a permanent seeding of the galaxy. These particles travel for millions of years, a silent rain of high-energy radiation that becomes part of the fabric of interstellar space. They contribute to the background hum of the cosmos, subtly influencing the chemistry of vast gas clouds and leaving their mark on the environment where future stars may one day form. Occasionally, one of these ancient travelers ends its epic journey right here. It arrives at the top of Earth's atmosphere, a single particle possessing the energy of a professionally thrown baseball, all compressed into a subatomic speck. Its collision with the air creates a fleeting, branching shower of secondary particles, a ghostly signature that our detectors on the ground can capture. By studying these rare events, scientists perform a kind of cosmic archaeology. They cannot visit the Magnetar directly, but they can catch the shrapnel from its explosion, using these messengers to decode the violent physics that launched them across the void. The chain reaction has now reached across the galaxy to touch our own world, delivering a whisper of a stellar cataclysm that occurred in the distant past. This invisible rain of cosmic rays is just one ripple in a much larger pond. The chain reaction now reaches into the most mysterious realm of all, the dark matter that forms the hidden skeleton of our galaxy. Picture the vast halo of dark matter that astronomers believe cradles the Milky Way. This matter is invisible, not because it is far away, but because it does not interact with light in any way we can normally detect. Its presence is only felt through its immense gravitational pull. But what if a Magnetar's blast could do what our telescopes cannot? Some compelling theories suggest that the initial fire hose of gamma rays, the very first shockwave from the Starquake, might be the key. As this radiation travels for thousands of years through the galactic halo, it could interact with the hypothetical particles that make up dark matter. The sheer intensity of the flare might provide just the right nudge to cause these elusive particles to briefly reveal themselves. The idea is that the energy could trigger a process where dark matter particles annihilate one another or decay into particles we can see, producing a faint, secondary flash of gamma rays that would arrive long after the main event. It is a staggeringly difficult signal to find, like listening for a single, specific whisper in a roaring hurricane. Yet this possibility transforms a Magnetar's violent outburst from mere destruction into a potential tool for discovery. We could be using the most energetic explosions in the universe to illuminate its greatest secret, turning a cosmic catastrophe into a flashlight to probe the invisible architecture that holds everything together. The very energy that shatters a star might one day help us map the shadowy framework of the cosmos itself. This stellar convulsion echoes through a far more fundamental medium than empty space. The sheer violence of a starquake with a slab of crust the mass of a mountain suddenly lurching does more than just blast radiation into the cosmos. It jolts the very fabric of reality. Einstein predicted that any accelerating mass creates ripples in spacetime, and a Magnetar's tantrum is the ultimate acceleration event. This is the source of a gravitational wave signal, a whisper of distortion that propagates outward at the speed of light. These are not waves of light or sound, but literal stretches and squeezes of the cosmic grid itself. For a fleeting moment, the space between stars would subtly warp, compressing and expanding as the tremor passes through. Detecting this signal would be like listening to the star's heartbeat, a direct transmission from its ultra-dense interior that light alone cannot carry. Our current observatories, like LIGO and Virgo, are tuned to hear the collisions of black holes and neutron stars, events of far greater mass and lower frequency. The quake of a single Magnetar produces a higher-pitched chirp, a frequency currently just beyond our hearing, but the next generation of listeners is on the horizon. A future space-based observatory like the proposed LISA mission would float in the quiet of interplanetary space, free from Earth's seismic rumble. Its laser arms would be millions of kilometers long, making it exquisitely sensitive to these high-frequency spacetime ripples, Catching the gravitational wave from a Magnetar flare would be a revolutionary moment. It would tear open a new window directly into the heart of the beast. We could finally probe the mysterious structure beneath that fractured iron crust, learning whether it contains exotic states of matter like superfluids or strange quark-gluon soup. This single signal could decode the inner workings of the most magnetic object in the universe, revealing secrets that have been locked away since its violent birth. But the chain reaction reaches even deeper than space-time itself. It touches the fundamental nature of what we consider empty space. The vacuum surrounding a magnetar is not truly empty. It is a seething quantum foam warped by a magnetic grip of impossible strength. This field is so potent it can force the void to spontaneously give birth to matter. According to the strange rules of quantum physics, pairs of particles and their antimatter counterparts can flicker in and out of existence everywhere all the time. Normally, they annihilate each other almost instantly. Yet near a magnetar, the magnetic field is so intense it can tear these virtual pairs apart before they can vanish, granting them a permanent reality. A single gamma-ray photon from the flare, carrying immense energy, can be transformed directly into an electron and its antimatter twin, a positron, pulled from the fabric of nothingness. This is pair production, a quantum miracle happening on an industrial scale. The flare does not just move through space, it actively populates it, generating a seething, superheated ocean of new particles known as a pair plasma. This plasma is then caught in the star's magnetic whirlwind, accelerated to near light speed. These particles themselves radiate energy as they spiral along the field lines, potentially creating new gamma rays that can then produce even more pairs. A single stellar tantrum can thus trigger a self-sustaining quantum cascade, where the macroscopic fury of the flare is directly fueled by the microscopic laws of particle creation. The line between a dying star's final scream and the birth of new matter from pure energy becomes astonishingly thin. This quantum cascade of new matter eventually dissipates, its energy fading into the background hum of the galaxy. But the chain reaction it began has one final, chilling destination. The ultimate reach of a magnetar's fury is not a nebula or a quantum field, but the fragile worlds that might harbor life. A planet like ours, orbiting a stable star within a few thousand light-years of such an eruption, would face an invisible apocalypse. The initial flash of X-rays and gamma rays would not just pass through the atmosphere, it would actively dismantle it. Striking the upper air, this radiation would tear apart the molecular bonds of our protective ozone, shredding the planetary shield that has taken eons to build. With that layer gone, the surface would be bathed in the unfiltered ultraviolet rage of its own sun. For any complex life, this would not be a slow decline but a swift, global catastrophe. The very chemistry of the air and water would change, triggering a chain of environmental collapse. The lush, living world would be effectively sterilized. This grim scenario is not merely a frightening story. Some researchers have looked back into our own planet's deep past, at the fossil record of sudden mass extinctions where the cause remains unclear, and wondered if a distant, dying magnetar could have been the culprit. It is a profound and humbling thought. The violent death throes of a star we would never see with the naked eye, an event isolated in the deep void, could reach across the galaxy to press a reset button on evolution itself. The universe is connected in ways we are only beginning to understand, where the fate of a world can be written in the tantrum of a star billions of years in its past. This cosmic reset extends to the very atmosphere surrounding the magnetar itself. Many of these stars are enshrouded by a pulsar wind nebula, a dynamic cloud of high-energy particles continuously blown outward by the star's furious rotation and magnetic field. This nebula is a constantly shifting environment, a stellar weather system of immense power. The arrival of a giant flare acts like a bomb detonating inside this delicate structure. The initial shockwave of radiation and high-speed particles does not just pass through the nebula, it violently interacts with it. The blast rams into the cloud, compressing the gas and dust with overwhelming force. This sudden squeeze intensifies the nebula's own magnetic field, tangling and amplifying it to new extremes. Simultaneously, the wave injects a fresh, furious population of particles into the system, like throwing gasoline onto a smoldering fire. The entire nebula responds by lighting up. It can brighten by orders of magnitude, shining brilliantly across the electromagnetic spectrum, from radio waves to X-rays. Its very shape can morph and twist under this new pressure. For astronomers, this is a rare and precious event. It is as if the universe has hit a reset button on a complex machine, allowing them to watch it reboot in real time. They can witness how the central engine, the Magnetar, communicates with and reshapes its extended environment. This transformation is not fleeting. The nebula's new, energized state can persist for centuries, a long-term monument to a single, brief moment of stellar violence. The chain reaction has now remodeled the star's immediate home, creating a living laboratory that will be studied for generations to come. That same shockwave, after traveling for millennia, can arrive at a stellar nursery. It finds a giant molecular cloud, a cold and dark cosmic womb where future stars sleep. This cloud is a fragile balance, a place where the inward pull of gravity is perfectly matched by the outward pressure of the gas. The incoming blast wave from the ancient Magnetar tantrum delivers a sudden, overwhelming push. It acts like a cosmic hammer, slamming into vast, tenuous filaments of gas and dust. The shockwave's immense pressure does not destroy the cloud, it sculpts it. It squeezes these pockets of material, forcing them inward. In moments that stretch across centuries, the cloud's internal pressure can no longer resist the new, external force. The balance is broken. Gravity, once held in check, now seizes control. The compressed pocket crosses a critical threshold, a point of no return. It begins to collapse under its own weight, spinning faster and heating up as it falls inward. A protostar is born, its fiery heart ignited by a shockwave from a stellar death that occurred light years away and eons in the past. A destructive event in one corner of the galaxy has directly triggered a creative event in another. This is the ultimate cosmic cycle, where the end of one star's story becomes the opening chapter for another. The universe takes the energy of destruction and channels it directly into the blueprint for new worlds, new suns, and perhaps one day new life. Yet the same force that ignites star birth can just as easily sterilize a cosmic cradle. While a shockwave might trigger collapse in a dark molecular cloud, its arrival at a young, developing solar system is an entirely different story. Picture a newborn star, a brilliant infant sun surrounded by a vast, spinning disk of gas and dust. This protoplanetary disk is a nursery for planets, a place where microscopic grains are slowly, gently clumping together to form the seeds of future worlds. Into this delicate construction site slams the blast from a distant Magnetar. The intense flash of radiation acts like a cosmic blowtorch, striking the disk and violently heating its outer layers. For the lighter elements, especially hydrogen and helium gas, this sudden energy input is too much to bear. These gases, which are the primary building blocks for gas giants like Jupiter and Saturn, can be stripped away entirely, boiled off into the void of interstellar space. The shockwave's pressure then plows through the disk like a tidal wave, churning the once orderly material into a turbulent chaos. The gentle dance of dust grains colliding and sticking together is replaced by violent, supersonic collisions that shatter nascent planetesimals back into dust. The carefully accumulating architecture of a young solar system is thrown into disarray. Where there was once a clear path for planets to coalesce in stable orbits, there is now only a scattered, stirred-up mess. A system that might have matured into a rich family of worlds, perhaps even one with a temperate, rocky planet in its star's habitable zone, could have its future rewritten in a single, violent instant. It could be left a barren collection of asteroids and stranded rocky cores, a permanent monument to a catastrophe that occurred light years away. The ultimate fate of countless potential Earths may hinge on the ancient, unseen tantrum of a dead star. This ongoing enrichment of the interstellar medium is a quiet but vital legacy of the chaos. The immense energy of a Magnetar flare does more than just push gas around. It actively forges new materials within it. In the searing heat and pressure of the blast wave, atomic nuclei are slammed together with such force that they can fuse, creating new, heavier elements. This process, known as nucleosynthesis, is not on the same grand scale as a supernova, but it operates in a uniquely intense environment. It might be one of the only places in the universe where certain rare, unstable isotopes can be synthesized. Think of it as a specialized cosmic workshop, producing exotic atomic ingredients that are difficult to create anywhere else. Simultaneously, the flare's radiation performs another crucial task. It acts like a universal solvent, striking tiny dust grains that float between the stars. These grains are like microscopic time capsules, containing elements like iron, silicon, and carbon that were forged in earlier generations of stars. The flare's energy blasts these elements free, vaporizing the dust and returning those heavy atoms back into the gaseous cloud. This is a fundamental act of cosmic recycling. It takes materials that were locked away and inert and makes them available again. They become part of the raw stock for the next cycle of star formation. Every new star that ignites and every rocky planet that forms around it is built from this enriched material. The iron in our blood and the calcium in our bones were once part of this interstellar dust, liberated and scattered by stellar events just like this. The violent end of one star ensures that the story of the next will be written with a richer, more complex vocabulary of elements. These subtle galactic fields form an invisible architecture that guides the entire galaxy. They are like the gentlest of breezes, yet they stretch across 100,000 light-years. When a Magnetar unleashes its fury, it does not merely send out a flash of light. It sends out a storm of its own magnetic force, woven directly into the expanding blast wave. This shock front carries a chaotic, turbulent magnetic imprint from the star's own unimaginably powerful field. As this wave plows into the thin interstellar medium, it does not just push gas, it actively braids and twists the weak, pre-existing galactic field line. The result is a localized knot, a region where the magnetic field is suddenly tangled and amplified. It is as if a single, deafening shout has created a permanent eddy in a quiet, flowing river. This distortion is not a fleeting phenomenon. The magnetic scar imprinted on that region of space can persist for eons. Now, consider that our galaxy has witnessed countless such eruptions over its long history. Each one leaves its own small, localized warp in the galactic fabric. The cumulative effect of these events, repeating over millions and millions of years, is a form of cosmic embroidery. The weak, large-scale field that we observe today, the one that guides cosmic rays and influences the birth of new stars, may be the stitched-together legacy of innumerable local cataclysms. A single star's violent end contributes a single thread to this galaxy-spanning tapestry. demonstrating how the most localized of disasters can, over deep time, weave the very framework that governs the cosmos. The violent light of a flare is more than a beacon of destruction, it is a message. For astrophysicists, this sudden eruption is a precious data stream, a direct transmission from the heart of a neutron star, a place forever beyond our physical reach. The oscillations and the precise timing of the X-ray and gamma-ray pulses that follow a starquake are not random noise. They are a cosmic sonogram, a rhythmic echo that maps the star's hidden interior. As these signals ripple outward, they carry the signature of matter under conditions that cannot be replicated anywhere on Earth. By meticulously decoding these vibrations, scientists can perform a kind of remote celestial surgery. They can probe the state of matter at supranuclear densities, a realm where the very idea of an atom ceases to have meaning. Here, gravity has crushed protons and electrons together, fusing them into an ultra-dense soup of neutrons, protons, and potentially even more exotic particles with names like hyperons. The ringing of the star after its quake reveals fundamental properties that were once pure theory. The data tells us about the stiffness of the star's iron crust, how it bends and breaks under unimaginable strain. It gives us clues about the viscosity, or the strange lack of friction within its hypothesized superfluid core, a quantum liquid that flows without any resistance. Most importantly, it illuminates the nature of the quantum forces operating at these densities, the fundamental interactions that hold the star together in a precarious standoff against its own immense gravitational weight. A single flare, in its brief, brilliant life, delivers a detailed report on the physics of the impossible. This cosmic downpour of energy becomes a direct threat to our own ambitions among the stars. The same chain of events that seeds the galaxy with new elements also broadcasts a lethal signal, one that could find its way to our spacecraft and astronauts. A Magnetar flare aimed at our solar system would unleash a storm of high-energy particles, a silent and invisible barrage traveling at nearly the speed of light. For satellites orbiting Earth, this would be an electromagnetic hurricane. The intense particle flux would slam into delicate microchips, inducing false commands and scrambling computer memory in what engineers call single-event upsets. More severe strikes could fry circuitry entirely, permanently disabling critical systems for communications, navigation, and Earth observation. The economic and scientific cost would be immense, a cascade of technological failure triggered by a stellar event thousands of light-years away. For any human explorers outside the protective cocoon of Earth's magnetosphere, the danger is far more personal. An astronaut on the lunar surface or during the long transit to Mars would have little warning. Their spacecraft's hull might offer some shielding, but the storm of particles would penetrate, delivering a radiation dose that could be lethal in a matter of hours. This is not a theoretical risk, but a concrete challenge that mission planners must confront. The very real possibility of such an event is a powerful driver for innovation. It compels us to develop new forms of radiation-hardened electronics, to design spacecraft with storm shelters lined with water or polyethylene, and to create advanced space weather networks that can give us those precious extra minutes of warning. Our journey into the solar system and our dreams of stepping onto other worlds are irrevocably tied to the tantrums of these distant magnetic beasts. The future of human spaceflight depends on our ability to listen to the galaxy's weather report and to build vessels that can survive its most violent storms. The story of these stellar outbursts may be written not only in the stars but also here on our own world. Scientists are learning to search for the faint, radioactive fingerprints of ancient Magnetar flares preserved in Earth's natural archives. Deep within ice cores drilled from polar glaciers, and in the annual growth rings of ancient trees, there could be a hidden record of past cosmic bombardments. When a nearby magnetar erupts, its storm of high-energy particles would have slammed into our atmosphere, transforming it into a vast nuclear reactor. This would alter the production rates of specific, rare isotopes. A sudden, unexplained spike in an isotope like nitrogen-14, or a sharp dip in the concentration of beryllium-10 within a single, dated layer of ice or wood, could be the telltale sign. It would be a chemical timestamp of a stellar cataclysm, marking the precise year a distant star's fury reached our planet. Finding such evidence would transform our understanding of galactic history. We could move from theoretical risk to documented fact, creating a timeline of these events over thousands of years. This historical context is crucial, allowing us to move beyond simple fear and toward a genuine statistical understanding of the threat. How often does our solar system pass through the line of fire of such a galactic storm? The answer lies buried in the ice and the trees, a quiet testament to the fact that our world is not an isolated island, but a participant in a much larger and occasionally violent cosmic story. One of the deepest cosmic mysteries just found its culprit. For years, astronomers were baffled by fleeting signals called fast radio bursts. These are incredibly brief blasts of radio energy, lasting just milliseconds but packing more power than our sun emits in 80 years. They seem to come from random points across the universe, billions of light years away, and their origin was a complete enigma. Then, in April 2020, everything changed. A known magnetar within our own galaxy, named SGR 1935 plus 215, suddenly flared. Telescopes detected a powerful X-ray burst, the classic signature of a starquake. But this time, something new arrived with it. At the exact same moment, a brilliant millisecond flash of radio waves was recorded. This was a fast radio burst happening right here in our cosmic backyard. That simultaneous detection was the smoking gun astronomers had been searching for. It proved for the first time that the intense magnetic tantrums of magnetars can directly generate these mysterious intergalactic signals. This single observation transformed our understanding. Magnetars were no longer just exotic local phenomena, fascinating but isolated to our galaxy. They were suddenly elevated to universal players, capable of producing a phenomenon we see echoing from the farthest reaches of space. The chain reaction of a single starquake now has a voice that can be heard across the cosmic void, a radio shout that travels for billions of years. To understand the scale of their influence, we must journey to the very beginning of everything. In the cosmic dark ages that followed the Big Bang, the universe was a featureless sea of neutral hydrogen gas, a silent and opaque fog. The first stars and galaxies eventually ignited, flooding the cosmos with their ultraviolet light and beginning the slow process of burning away this primordial mist, a pivotal era known as the epoch of reionization. But some of these first stars were behemoths, living fast and dying young in spectacular supernova, leaving behind the universe's earliest magnetars. Their unique contribution may have been decisive. While the ultraviolet light from the first stars struggled to penetrate the densest regions of gas, a magnetar's tantrum produced something different, a fire hose of hard X-rays. This high-energy radiation is a cosmic power drill, capable of boring through thick clouds of primordial hydrogen that would have stopped ordinary starlight in its tracks. Where a gentle ultraviolet glow might be absorbed, a magnetar's X-ray flare could travel deep into the heart of a gas cloud, striking a single atom and blasting its electron away, effectively ionizing it and helping to clear the cosmic fog from the inside out. This means these magnetic monsters were not just local disasters, they were potential architects of cosmic transparency. Their violent outbursts could have carved the first clear channels through the universal murk, helping to end the Dark Ages and forge the luminous, structured cosmos we observe today. The very energy that shatters worlds may have been instrumental in creating a universe where we can even see them at all. The star's fury can even seize control of its own cosmic exhaust system. Many of these objects, including some magnetars, launch incredibly focused beams of matter known as astrophysical jets. These are not gentle outflows but tightly collimated streams of particles screaming outward at nearly the speed of light. When a major flare erupts from the star's surface, it sends a violent shock wave right through the heart of this delicate structure. Think of it as a sudden, immense power surge hitting a perfectly tuned fire hose. The results are dramatic and unpredictable. The jet might respond by flaring to incredible brilliance, its light amplified by the fresh injection of raw energy. In other scenarios, the blast's chaotic magnetic fingerprint can push the entire jet, forcing it to wobble or even change its direction entirely, like a garden hose knocked by a sudden blow. In the most extreme cases, the star's tantrum is so overwhelming that it can temporarily overwhelm the jet's launch mechanism itself, shutting down this cosmic engine for a brief period before it sputters back to life. For astronomers, this violent interaction is a priceless opportunity. The process of launching and focusing these relativistic beams is one of the most complex in all of astrophysics, a phenomenon seen on a gargantuan scale shooting from supermassive black holes at the centers of galaxies. But those systems are vast, slow, and difficult to observe in detail. A Magnetar's jet, however, is a scaled-down, high-speed laboratory. Watching how a flare disrupts, re-energizes, or redirects this stream gives us a front-row seat to the fundamental physics of how the universe channels matter and energy across interstellar space. The ultimate power of a Magnetar flare reaches beyond the destruction of worlds and the birth of stars, touching the very rules that govern reality. At the heart of this stellar fury lies a profound mystery that has puzzled physicists for generations: the unification of Einstein's general relativity with the strange laws of quantum mechanics. These are the two foundational pillars of modern physics, and they refuse to speak the same language. One describes the grand, smooth curvature of space-time, while the other governs the frantic, probabilistic dance of the subatomic world. A magnetar, with its unimaginable density and magnetic fields, creates an environment where both of these extremes are pushed to their absolute limits. It is a place where the warping of space-time is immense and the quantum behavior of matter is inescapable. This makes the violent flash of a flare more than just an explosion. It becomes a unique cosmic testbed. For a fleeting moment, conditions are ripe to test theories of quantum gravity, the long-sought framework that would finally marry these two disparate descriptions of our universe. One compelling idea suggests that space-time is not the smooth continuum we perceive. At the tiniest conceivable scales, a distance a trillion times smaller than an atom, the fabric of reality may be churning and foamy. This quantum foam would be a seething sea of virtual black holes and wormholes, constantly bubbling in and out of existence. Under normal circumstances, this froth is utterly undetectable. But the gamma rays from a Magnetar flare, traveling across thousands of light years, could carry its signature. The theory predicts that higher energy gamma rays would interact with this foam just slightly more than their lower energy counterparts. Over an immense cosmic journey, this minuscule interaction could cause a tiny but measurable delay in their arrival time. It would be as if the highest energy photons were wading through a thicker medium, arriving at our telescopes a fraction of a second after the others. Detecting this delay would be like finding a single distorted grain of sand on a beach that spans the galaxy. It would be a monumental achievement, providing the first experimental evidence that the smooth stage of spacetime is an illusion and that at its heart reality is grainy. A single stellar tantrum, observed with exquisite precision, could therefore illuminate the path to the theory of everything, using the most violent objects in the cosmos to answer the most fundamental questions of all. These stellar fireworks do more than reshape the cosmos, they capture something deep within us. The announcement of a Magnetar flare in a distant galaxy is not confined to scientific journals. It ripples instantly through our global culture, becoming a headline on a news site, the subject of a breathtaking documentary, and a topic of wonder in a science classroom. A teacher might project an artist's impression of that cracking stellar crust onto a screen, and in that moment, a young student's perception of the universe shifts. The abstract concept of magnetic fields becomes a tangible, awesome force, a power that can shatter a star. That single moment of awe can be a powerful catalyst, sparking a question that leads to a book, then a project, then a career. The violent, distant death of a star becomes a personal invitation to explore. This is how the cosmos recruits its next generation of interpreters, the physicists who will one day build a better gravitational wave detector, the engineers who will design radiation-hardened spacecraft for Mars, and the astronomers who will find the next great cosmic mystery are all out there right now. They might be the ones watching that documentary, their curiosity ignited by the story of a stellar giant's final, magnificent tantrum. The chain reaction completes its journey, moving from a shiver in spacetime to a spark in a human mind, ensuring that our quest to understand the universe continues to burn brightly. The same physics that tears a star apart is now helping us build a better future. Our struggle to capture the fleeting tantrum of a magnetar is a powerful engine for innovation here on Earth. To catch these bursts, we must launch observatories beyond our atmosphere, where our planet's protective blanket does not block the high-energy X-rays and gamma rays. This demand pushes engineers to the absolute limits. They design detectors of astonishing sensitivity, capable of registering a single photon from a source thousands of light-years away. The materials used for these instruments must withstand the harsh radiation of space while being incredibly lightweight, driving breakthroughs in advanced composites and novel semiconductors. The data stream from these telescopes is a fire hose of information, a chaotic mix of cosmic signals and electronic noise. To find the 1 in a billion signature of a Magnetar flare, scientists create brilliant algorithms, complex filters that can spot a specific pattern in an ocean of randomness. These same computational tools, forged in the hunt for stellar explosions, are now saving lives. They are used in medical imaging to enhance the clarity of MRI and CT scans, helping doctors detect tumors at their earliest, most treatable stages. The pattern recognition software can also be adapted to find subtle, anomalous signals in global financial markets, identifying potential fraud or systemic risks long before they trigger a crisis. Even the theoretical work is paying dividends. The study of the superheated, magnetically dominated plasma around a magnetar is a natural laboratory for understanding how matter behaves in these extreme states. This knowledge is directly applicable to one of humanity's greatest quests, the pursuit of controlled fusion energy. To contain a miniature star in a reactor on Earth, we need to master the behavior of plasma within powerful magnetic fields. The violent experiments conducted by nature on distant magnetars provide the crucial data and theoretical models that bring our own clean energy dreams closer to reality. The quest to understand a cosmic cataclysm quietly builds a legacy of tangible progress, proving that by looking up at the most destructive forces in the universe, we often find the tools to build a better world. This raw power forces a profound shift in perspective. We build our civilizations, our histories, and our technologies on a planet that feels immense and permanent. Yet our entire world, with all its complexity, is a temporary arrangement of atoms orbiting a stable star in a quiet galactic neighborhood. A single eruption from one of these magnetic monsters, an event we could neither predict nor prevent, carries more energy than our species will ever generate across its entire existence. This is not a universe crafted for our convenience or safety. It operates on a scale and with a ferocity that is entirely indifferent to the delicate balance of life. The knowledge that such forces are woven into the fabric of our galaxy instills a deep and necessary cosmic humility. It shatters the illusion that humanity sits at the center of the cosmic story, challenging the anthropocentric view that has shaped so much of our history. We are not the protagonists of the universe, but fleeting observers, inhabitants of a dynamic and often dangerous stage. This realization is not meant to inspire fear, but to foster a clearer, more honest understanding of our true place in the grand scheme. It reframes our existence, highlighting both our profound fragility and our remarkable capacity to perceive and comprehend these vast, impersonal forces. This perspective can fundamentally shape how we approach our own future, encouraging a greater awareness of existential risks and a deeper appreciation for the precarious, beautiful oasis we call home. This single flare generates a fire hose of information, a digital flood that can overwhelm our capacity to understand it. A single event can produce petabytes of data from a global network of observatories, both on the ground and in space. To put that in perspective, 1 petabyte is enough to store over 200,000 high-definition movies. This is the new frontier of astronomy, a field now grappling with a monumental data deluge. Simply storing this much information is a colossal task, requiring vast server farms and sophisticated archival systems. But the real challenge is not just holding the data, it is making sense of it. This is where the new science of astroinformatics emerges. Scientists are now training sophisticated machine learning algorithms to sift through this digital universe, teaching computers to recognize the subtle signature of a starquake buried in a sea of random cosmic noise and instrumental glitches. No single institution can handle this alone. The effort has spawned global collaborations, creating distributed computing networks that share processing power and storage resources across continents. It is a worldwide web dedicated solely to decoding the universe's most violent messages. Yet, even with the patterns identified, the final step is human comprehension. How do you present the complex, multi-wavelength story of a stellar explosion in a way a researcher can intuitively grasp? New data visualization techniques are being born from this need, transforming abstract numbers into dynamic, three-dimensional models that let scientists virtually fly through the aftermath of a flare. This entire digital ecosystem, from the algorithms to the global networks, is being forged for a glimpse into a few fleeting seconds of stellar violence. The chain reaction of the Magnetar has now sparked a parallel revolution here on Earth, one that is fundamentally transforming how we do science and pushing our digital infrastructure to its absolute limits. This coordinated hunt transforms a single flash in the sky into a rich, multidimensional story. This is the essence of multi-messenger astronomy, a revolutionary approach that treats a cosmic event like a symphony, where each signal is a different instrument playing its part. A Magnetar flare is a perfect conductor for this symphony. Its initial starquake might be captured as a spike in gamma rays by one satellite, while another observatory records the resulting X-ray afterglow. The tremor itself could, in theory, send out a faint, high-pitched chirp of gravitational waves, a stretch in space-time that future detectors might one day feel. Even the ghostly neutrino, a particle that barely interacts with matter, could potentially stream from the star's superdense core during its moment of fracture. Each of these messengers carries a unique piece of the puzzle. Light tells us about the surface and the immediate environment. Gravitational waves would whisper secrets about the interior dynamics and the crust's oscillation. Neutrinos could offer a direct, unfiltered transmission from the heart of the quantum maelstrom. By combining these disparate signals, astronomers can perform a kind of celestial triangulation, not just in space, but in the very nature of physical reality. They can cross-check theories, validate models, and discover connections that would be invisible to any single observatory. The study of a single flare becomes a collaborative, global experiment, weaving together data from telescopes orbiting Earth, detectors buried deep in Antarctic ice, and laser interferometers suspended in vacuum chambers. This holistic view proves that to understand the universe's most violent acts, we cannot rely on a single sense. We must learn to see, hear, and feel the cosmos all at once, discovering that the true narrative of a star's death is woven from many different threads of information. Yet this power seems to follow no predictable schedule. Why does one Magnetar scream into the void repeatedly, while its neighbor, seemingly identical, remains locked in a deep and silent slumber for centuries? This disparity is one of the great unsolved puzzles in modern astrophysics. The answer is not a single, simple switch, but a complex and delicate dance between the star's internal engine and its rigid outer shell. It is a celestial balancing act. On one side, you have the immense twisting force of the magnetic field, constantly applying stress. On the other, you have the solid iron crust, a crystalline structure trying to contain that energy. The final participant is the star's superfluid core, a bizarre quantum liquid that flows without any friction whatsoever. This core can suddenly rearrange itself, creating microscopic vortices that transfer stress to the crust in unpredictable jolts. A magnetar with a perpetually unstable crust riddled with weak points and faults might exist in a state of constant hair-trigger tension. The slightest shift from the superfluid below or a further twist of the magnetic field is enough to cause a rupture. This star would be a frequent flarer, its life a series of violent, smaller outbursts. Another magnetar, however, might possess a thicker, more monolithic crust. It could act like a perfect pressure vessel containing the internal strain without a single crack for millennia. The magnetic field continues to wind tighter and tighter, storing energy on a truly catastrophic scale. When this star finally does break, the resulting flare would be an event of legendary proportions, a once-in-a-galactic lifetime explosion. Solving this mystery is more than an academic exercise. It is the key to predicting the behavior of these cosmic powerhouses. By understanding why they flare when they do, we could one day create a galactic hazard map, identifying which stars pose the greatest long-term risk to interstellar space. The quiet magnetar may simply be biding its time, a coiled spring in the darkness, waiting for the perfect moment to unleash a chain reaction that will echo for millions of years. Our next window into this cosmic drama is already opening. A new generation of observatories is being built, each designed to catch a different fragment of the Magnetar's story. Together, they will transform these brilliant flashes from fleeting mysteries into comprehensive chronicles of extreme physics. The James Webb Space Telescope will act as a cosmic historian, studying the infrared light emitted by dust clouds flash heated by a flare. This faint, long-lasting echo will reveal the composition and quantity of material that was vaporized, telling us what the blast wave encountered and destroyed. Meanwhile, the Athena X-ray Observatory will function like a high-speed microscope for superheated gas. It will map the million-degree plasma forged in the explosion, tracking its motions and temperatures with a clarity we have never before possessed. On the ground, the Cherenkov telescope array will serve as our ultra-high-energy sentinel. It will search for the faint, bluish glow created when the most energetic gamma rays from the flare strike our atmosphere, probing a spectral range that has remained largely invisible until now. And on the horizon, space-based gravitational wave detectors will finally give us ears for the Starquake itself. They will listen for the subtle ringing of space-time as the Magnetar's crust fractures, providing a direct sonogram of the event that started it all. This coordinated sensory assault will weave light, radiation, and space-time ripples into a single, unified narrative. We will no longer just see the flash, we will witness the entire life cycle of the chain reaction, from the first crack in the star's crust to its final, fading whisper across the galaxy. This same ferocious energy density leads us to the edge of known physics, to a speculative frontier where the local and the cosmic might intertwine. Some theoretical work has begun to ponder a startling connection. The vacuum energy that seems to fuel a Magnetar's tantrum, the seething quantum foam from which particle pairs are torn, is a localized phenomenon of almost unimaginable strength. Yet, cosmologists have their own profound mystery: dark energy, the repulsive force causing the entire universe to expand at an accelerating rate. The leading hypothesis for dark energy's source is the quantum vacuum energy of empty space itself. This presents a staggering puzzle, a cosmic mismatch of epic proportions. The vacuum energy calculated from quantum theory is a staggering 120 orders of magnitude too large to match the observed rate of cosmic expansion. It is the worst prediction in the entire history of physics. So, could a Magnetar's flare be a clue? Is the vacuum energy powering its outburst a hyper-concentrated, ultra-strong version of the very same force that is stretching the fabric of the cosmos? The idea is, by all accounts, highly speculative and far-fetched, but its value lies not in its immediate plausibility, but in its sheer audacity. It demonstrates how studying the most extreme objects in the universe does not just answer existing questions, it forces us to ask new, more fundamental ones. It pushes us to consider whether the laws governing a dying star's final scream are intimately linked to the destiny of the entire universe, connecting the infinitesimally small with the infinitely large in a single, breathtaking line of inquiry. But could the echo of a single star's death truly shape the largest structures we know? The cosmic web is the ultimate architecture of reality, a vast network of galaxies strung along invisible filaments of dark matter, separated by immense, empty voids. On this scale, the energy of a single Magnetar flare seems vanishingly small, a drop in an ocean of cosmic power dominated by supernova and the monstrous engines of active galactic nuclei. Yet their unique voice might find a purpose in the quietest places, in the sparse outskirts of galaxy clusters or deep within the million light-year emptiness of cosmic voids. The ambient energy is incredibly low. Here, the hard X-rays from a Magnetar flare would not be diluted by a crowd of other signals. This penetrating radiation could travel for eons, striking the tenuous gas that drifts between the web's strands. The energy might be just enough to gently heat that material, preventing it from cooling and collapsing under its own gravity to form new dwarf galaxies. In this subtle, long-term way, these stellar outbursts could act as cosmic maintenance workers, their combined influence over billions of years helping to preserve the delicate balance of the voids, ensuring they remain truly empty. This idea stretches the chain of causality to its absolute limit, suggesting that the localized fury of a dead star might contribute in a tiny but real way to the maintenance of the universe's grand design. The same shockwave that sterilizes one world might seed another. This paradox lies at the heart of an idea called panspermia, a planet rich with microbial life, orbiting within a few dozen light-years of a magnetar eruption could experience a violent liberation. The initial flash might strip away the atmosphere, but the following blast wave could act as a cosmic catapult. It would slam into the planet's surface, not just churning the rock, but launching fragments of the crust clear of the planet's gravity. These ejected boulders, some the size of mountains, would become interstellar arcs. Trapped within their protective, stony interiors, dormant microorganisms like extremophile bacteria could potentially survive the cold and radiation of deep space. Their journey would be a slow drift across the galactic ocean, lasting for millions of years until a chance encounter with a new, young planetary system. There, a meteorite impact could deliver these ancient passengers to a fertile new world, jump-starting the biological chain of evolution in a distant solar system. A single act of cosmic destruction could inadvertently become the gardener of life across the stars. This concept takes an even more profound turn with a far more speculative theory, directed panspermia. Imagine an advanced civilization that has achieved the ability to monitor the galaxy for threats. Their astronomers detect the precursor signs of a nearby magnetar preparing for a cataclysmic flare, an event that will inevitably scour their world clean. Facing an unavoidable end, they make a conscious choice for legacy. They would not build shelters, but instead construct durable, guided capsules, each one a tiny biological library containing the genetic essence of their world's life. These vessels would be launched on precise trajectories toward promising, habitable star systems, a final act of cosmic sowing. In this deeply poignant scenario, the magnetar's flare becomes a tragic catalyst. It transforms from an agent of pure annihilation into an unwitting trigger for the deliberate spread of life, a forced diaspora on a galactic scale. The chain reaction of a dying star could, in its final, indifferent act, compel intelligence to ensure that biology, in some form, endures. From a single crack in a star's crust, we have traced a chain reaction that stretches from the quantum void to the galactic web. This journey reveals a cosmos of profound interconnection, where the universe's most violent tantrums are woven directly into the tapestry of existence. Magnetars are far more than distant curiosities. They are active, dynamic players in the ongoing story of our cosmos, their outbursts subtly influencing the birth of stars, the chemistry of life, and even our quest to uncover the universe's most fundamental rules. The next time you gaze at the quiet, familiar night sky, remember the incredible, hidden power slumbering within it. That tranquility is a beautiful illusion, masking a dynamic and often ferocious reality just waiting to be discovered. If you want to join us as we continue to decode these cosmic mysteries, consider subscribing for our next journey into the unknown.